it is my pleasure to introduce my good friend and accomplished colleague, Dr. Walter Mooney of the United States Geologic Survey. There's a wide range of geophysicists out there, and what I like about Walter is he applies his geophysical tools to problems of interest to geologists. There are many geophysicists that do not, or if they do, they make it so opaque that no poor geologist can possibly understand what they're doing. Walter doesn't do that. His papers are focused on big problems in especially the crust, and as you'll see from his lectures, this time for the remainder of this meeting and on Wednesday, that he addresses problems of deep interest to the geologic community. And I encourage you to look him up and learn more about him. Don't go to his USGS website because it's woefully out of date, but go to his Google Scholar profile. Or Walter, do you have a Wikipedia entry?
Yes, I do have a Wikipedia entry with key papers listed.
Yeah, so I encourage you to go there. You'll be impressed by this remarkable scientist. And with that, Walter, thank you very much for talking to us, and we look forward to what you're going to tell us.
Thank you for the introduction, Bob, and nice to meet all the students. If I have done any useful work, it's mostly because of the help that I've gotten from others and my colleagues who have worked with me. So I don't claim credit for all the work that's been done. We're going to talk about geophysical techniques. Okay, folks, nice to meet all of you. As I said, this is my research group in California, and you can see people sitting at our lunch table. We would have regular parties. The people that you see there are from Kyoto University in Japan. The Japanese fellow worked with me for 3 years and did his PhD and got his degree from Kyoto. People from Europe, Ireland, Los Angeles, and many other locations, many Chinese and Korean students and others. So what we're looking at is the interior of the Earth and the hazards that are generated by plate tectonics and mantle convection. And here's this diagram, very colorful and illustrative diagram that shows you some of the dynamics of the Earth. So just to give you an overview, I sometimes get called to deal with crises around the world, earthquake, tsunami, and volcano crises, and here are some of the places that I've gone. Now, the thing that I would like to emphasize to everyone is that what you read in the newspaper or on your cell phone does not tell you the correct story of a crisis. Let me just give you one simple example. If there's an earthquake in Ecuador, you may see a picture of a building burning, and you get the impression that this earthquake has caused widespread fires. But in fact, it will only have been one building that was on fire, but they keep repeating that same image, and you get the wrong impression. So you need to go and study these things with boots on the ground. The same is true of geological structures. If you read in a book that the structures are dominated by thrusting, if you go into the field, you may find that in fact a lot of normal faulting is also taking place. Well, these are some of the places that I've been responding to crises, and I'll give some examples. So working in Africa, these are the countries that I've worked in, and there are a lot of earthquakes in Africa and active volcanism as well. If we look at the Red Sea and Saudi Arabia, there's active rifting taking place in the Red Sea, and this causes volcanism in Saudi Arabia. So here we see these volcanics, which are not far from the Red Sea. And in the upper picture, you can see these cinder cones. These cinder cones are located next to the city of Al-Madinah. Al-Madinah is a holy city in Islam because it's the location of the first mosque of the Prophet Muhammad. The idea was that they would remove the smaller syndicones and expand the city on top of the volcanic area. And USGS was called in to recommend whether or not that would be a good building policy. So what did we have to do? What we had to do was determine what was the frequency of volcanic eruption and how old, or how young, you might say, these volcanoes are. So I have a question for Professor Bob Stern. How did we get the age of the volcanics, of these basaltic volcanics?
Oh, the main work was done by the USGS and maybe the French BRGM, applying the potassium argon or argon geochronology, wasn't it?
Exactly correct. Okay, you get an A+ on that one.
Yay!
It's difficult to date a basalt, and you have to, the technique that was developed by Alan Cox and others uses potassium argon and argon. And we found that these volcanics were quite young, and we told the Saudi government, do not expand your city to the volcanic area. Do not use a bulldozer to remove the volcanics and build apartment houses on top of the volcanic vents. This is too dangerous because the volcanoes are very young. 11,000 years was the age. Well, you can barely see even these tiny little islands that form the Union of Comoros. These islands are in between Madagascar and Mozambique. It's a volcanic archipelago like Hawaii. And they have an active volcano, and the volcano began to spill lava over the side. And the US State Department asked USGS to get over there and advise the government whether they needed to evacuate the city. So I went over and we put out solar panels and seismometers and transmitted the data back from the volcano center to the city and built a volcano monitoring system. What happened was the volcano began to calm down and it was not necessary to evacuate. You can see me in the field there. I'm the guy with the hat, and I have lots of helpers. And we were putting out simple seismic stations with FM radio transponders. So this was a simple volcano monitoring system, which is still operating today. In Indonesia, we have lots of subduction zones, and you'll recognize the symbol there, the lines with the teeth on them, with the Sunda Trench subducting beneath much of Indonesia, and a very complicated tectonic organization in the center of the slide with multiple subduction zones facing in different directions. And what we are doing in Indonesia is building a tsunami early warning system. So when an earthquake occurs, we determine whether it occurred at the subduction zone and was shallow. If it's a shallow thrust, then it has the potential of moving the water column and generating a tsunami. So tsunamis are a big hazard, and as you may recall or may have heard, there was a big earthquake, magnitude 9, in 2004, which killed 250,000 people in the Indian Ocean basin. So tsunami warning systems, these are early warning systems. You have about between 10 and 30 minutes to evacuate the coast if you get your warning system out, if you get the warning done early enough. So here's the seismicity of Indonesia. The blue is the shallow seismic energy. The red are the very, very deep earthquakes that are down in the subducting plate. And the blue are the earthquakes that can generate strong tsunami waves. So in addition to doing this kind of work, we also train others to work independently. So this is the training of tsunami warning staff in Jakarta. These are not students, these are young workers, and they are able to give the tsunami warnings. Yes, thank you. I see someone has a question, and I'd be happy to hear that question.
Yeah, I apologize. It was just a couple slides ago when you were showing the subduction zones. And I'm sure I should know this, but I didn't understand what is the difference between the arrows that are filled in and the arrows that are not filled in.
Good question. Thank you. And that's a sharp eyes. The subduction zone with the arrows not filled in is continental subduction. That's the continental margin subduction, and the black are oceanic. So for the purposes of this lecture, of the lecture that I was showing before, if you have an oceanic plateau that's reaching the trench, then, or the continental margin of Australia, it's open subduction. Thank you.
Well, now you've got me really confused. So, I mean, it's the continental is subducting underneath an ocean plate.
Oh yeah, I'm glad that you commented on that and admit to being confused. Yes, the continental margin of northern Australia is subducting underneath an oceanic plate, and it's gone down 220 kilometers based on reconstruction. And so the Banda subduction zone is continental ocean subduction. And it's very rare. If you want to read more about it, there's a beautiful paper in Geospheres, and the first author is T-A-I-T, and Tate, and the key author is from the University of Pittsburgh. Oh my goodness, I've forgotten her name. I'll think of it later.
Is that part of the continent just denser than normal continental?
Oh, I see. So you have a long oceanic slab that's pulling it down, and the continent is connected to the oceanic slab. So the dynamics of the system are being driven by an ocean. Bob, do you remember the structural geologist that worked with Brian Wernicke? She was a professor at Princeton, and then she moved to Pittsburgh.
Lee Royden? Is that Lee Royden?
No. It was MC. Anyway, but the first author
Macquarie.
is
Nadine Macquarie.
Yeah, Macquarie. What's her first name?
Nadine
Macquarie. You got it. It's a beautiful paper, and it's showing continental subduction. It doesn't happen everywhere, but of course we know that continents can subduct because we get these ultra high pressure metamorphic rocks like in the Alps and some other places. But I better keep moving. So we do hands-on training of the students, and this is a lot of work because you have to make an exercise where they're locating earthquakes or doing earthquake tsunami early warnings on the desktop, and that takes quite a bit of thinking. Sometimes volcanoes erupt and very suddenly, and the Honga Tonga eruption was about 2 years ago, and it was one of the largest eruptions ever took place. And the Tonga government contacted us and said, "Hey, we need a volcano warning system. What can you do to help?" So that means you're putting out GPS, global position satellite systems, on the volcanoes where they're accessible, and putting out seismic stations to monitor the activity. So the location of this volcano is here north of New Zealand and to the west of the Tonga Trench. So the volcano was growing and was observed, and these clever people, Garvin, 2018, 4 years before the eruption, predicted that there would be unrest. And you can see the big volcano was just part of a much larger volcanic caldera. The entire caldera, you can see, is quite large in this image, and it's just the northern edge that was the eruptive source. So when it went off, bang, it went off, and the ash cloud went up 10 kilometers and generated a big tsunami wave that inundated Tonga. And they did not have an adequate tsunami warning system at that time. Okay, so what about geophysics? We're using math and physics to solve real world problems. We also concerned with the evolution of the Earth, the solar system, and even the universe by comparing the Earth to other planets, most particularly Mars and Venus. And we do our field work nationally and internationally. And it's important for us to give training to others so they learn from what we've learned and to publish our results. So geophysical techniques useful for tectonic studies. We're going to start with seismicity, identifying the location and significance of faulting, and then move on to structural seismology. Earthquakes. The location of the earthquakes. The occurrence of an earthquake is the clearest sign of ongoing tectonic activity. The epicenter is the location at the surface, but earthquakes don't occur at the surface. They have a focal depth, and we call that the hypocenter. Like a hypodermic needle is something which goes under the skin, so it's a hypocenter. And the hypocenter could be as deep as 660 kilometers. So this diagram is very simple, and yet there's much to discuss here. It shows a normal fault, and the focus of the earthquake is located at the hypocenter, and the projection of the earthquake focus is the epicenter. Now, when an earthquake occurs, the rupture actually propagates. If you throw a stone at a glass window, the impact point will initiate a crack in the window, and the crack will then propagate over time. It's very rapid, of course, but it will propagate over time across the window pane, stopping at some point. So an earthquake is not 2 blocks that move all uniformly. It's a rupture which propagates. And this fault scarp here, or the fault trace, would the earthquake would propagate, say, in this case, to the north, into the page at a certain rate. There are also, in addition to those kind of normal faults, there are deep earthquakes. And seismological observations began in earnest with seismographs around 1880. 1889 was the first time we recorded a distant earthquake, and Wadati and Benioff were among the first to identify deep earthquakes. Hugo Benioff was a professor at Caltech, and the interesting aspect of him was that he never had a student. At some universities, you can teach your entire career, but you never take a PhD student. Now, I point out that there is one other famous scientist who taught for a long time but never had a student, and that is Albert Einstein. Einstein never had a student, and it's an interesting observation. Some people don't do it. Okay, so now we get the big picture. Of course, what we're looking at here is a cross-section showing plate tectonics with mid-ocean ridge in the center of the cartoon, magma coming up and forming the oceanic plate. And the earthquakes are these red stars that range from right at the trench there where it says oceanic trench, and they continue deep into the mantle. And there are a number of other elements of this diagram that showing magma and so on, but that's not our focus right at the moment. We'll come back to that aspect. So here's Benioff's early diagram from 1949, showing these his early attempts to identify, to plot, and to identify these deep earthquakes. And keep in mind, this is really frontier work. We're back at Tonga Kermadec, where the volcano that I began the lecture with, and the earthquakes epicenters are shown on the left-hand side, spread out. But it was only when he made a cross section that he began to see that there was a dipping plane. And there was no way in 1949 to explain this dipping plane because plate tectonics had not yet been introduced. So at that time, the belief was that this was just a normal fault. People didn't know about plate tectonics.
Out of curiosity, in 1949, what kind of equipment were they using to measure this data, to collect this data?
That's a good question. So the question was, how the heck did they locate these earthquakes and which equipment were they using? So these were widely dispersed seismographs. The nearest seismograph could have been in New Zealand, one station in New Zealand. In Indonesia, there was the station Batavia. There were seismic stations in almost all the main continents, and in a very, very few cases on some islands. So if we look at this diagram, you can see that things don't fall on a plane, and the scale is on the horizontal scale is 0 to 1,000 kilometers, and some of the earthquakes are mislocated off of the black line by 200 or 300 kilometers. So they couldn't locate the earthquakes very well. And it was only later that they were able to locate them better. Now we're installing new seismic stations in Tonga and Fiji these days because we're still trying to improve the quality of the locations. Okay, so again, the depth of the focus of the earthquake is the hypocenter, and the epicenter that we showed on the previous slide is just the surface expression. Well, how do we locate these earthquakes when we have far distant seismographic stations? As you can see on the upper left, the earthquake occurs at its focal point, the hypocenter, and it travels to a distant station, and the arrival time will be recorded by the P wave, the compressional wave, and the shear wave, which is slower. So the time difference between the S wave, which may take, let's say, 7 minutes to arrive, and the P wave, which may be 4 minutes to arrive, that gives you the distance distance to the earthquake. If a bus leaves a train station and starts down a straight road and going at 50 miles an hour, and I leave the train station on my bicycle going 20 miles an hour, as the time lapses, the bus and I will get larger, further and further separated in time. And if you measure the distance between me and my bicycle and the bus, you can tell how many minutes it's been since we left the train station, because it's increasing with time. So the greater the separation between P and S wave, the more distant is the earthquake. So the distance is measured by this difference. And if you have 3 seismic stations, you can actually triangulate on the location. So need 3 far separated seismometers to locate an earthquake. And you can see the red is the P wave, the compressional wave coming in. The S is the S wave. And in the diagram on the right, 3 stations have located that epicenter. Where the circles intersect is the station location. And if you have 20 stations, you can do an even better job because you reduce the uncertainty. So the first motion of the earthquake at a station refers to whether whether the ground moves up or moves down. On the left, there's the first motion, which is a push, the upward motion, and on the right, under letter B, is the first motion, which is a down. That's the earthquake, the ground moving away from the seismographic station, and this allows you to get the focal mechanism, the direction of motion on the fault. So if you have an earthquake plane and this one moves this way, it's kind of a punch at you, and this moves the seismograph up like figure A. So more than just the arrival time, the motion at the seismograph is informative as well. And then we have all the different kinds of earthquakes, sliding faults, which are called strike slip, normal faults, which are the downward sliding one. That's example number 2, a so-called reverse fault, which is due to compression, and oblique reverse. So these you'll find in the Carey book, so you can read that in detail. The main point is that with enough seismic stations, we can determine the focal mechanism. Everyone gets confused when they hear about an earthquake. Well, there was a magnitude 7 earthquake in Japan. Well, Japan says it was a magnitude 6.8, and Germany says it was a 7.2. All these different magnitudes have to do with how they're measured. They're usually pretty close, but if you hear different magnitudes from different agencies, it's because they've been measured in different ways. The most standard magnitude today is number 3 on the list, the moment magnitude, MW, and it's related to the amount of slip on the fault and the area that has slipped. So you can read these different magnitudes on your own time, and do not be confused if you hear slightly different magnitude numbers. They refer to different instruments that measured the earthquake, and they don't agree exactly the same. So the Great Sumatra earthquake of 2004, why are we showing this one? Well, primarily because it caused such a huge tsunami wave. It occurred in Sumatra, northern Sumatra, not far from the Andaman Islands. And it was a very big earthquake that ruptured 1,300 kilometers. The magnitude was a 9. That's about as big as they get, 9 or 9.2, 9.3. And it was right on the east side of the Indian Ocean, and it generated huge tsunami waves that inundated all the beaches in the Indian Ocean basin. So the focal mechanism of the northern Sumatra earthquake that was first determined was for a thrust fault. And this is very important because the nature of the thrust faulting causes the seafloor to large displacement on the seafloor, and that's what will cause the big tsunami. Obviously, if you have a simple strike slip fault, just sliding fault offshore, it's not going to move the water very much, and there will not be a large tsunami. So we want to know this focal mechanism, the nature of the faulting, because that tells us how high is the risk. So one of the training that we do in Indonesia is teaching people how to determine the earthquake source mechanism, or the so-called focal mechanism, so they can be aware of whether there's a tsunami potential. So you can see all of these mechanisms. There are so many shown here. They are half white and half black. These are all thrust faults in Central America, and all of these are related to the subducting oceanic plate going down beneath the continent. And all of these have the potential of generating a tsunami if they're shallow.
Hey, Walter, can we go back? I wanted to draw
Sure.
their attention to the ones in the Northeast that look different. Those are strike slip mechanisms. You've got a strike slip fault that's going through there.
Yeah, that's the fault that generated a big earthquake in the Cayman Islands a week ago. It's a strike slip fault on the northern boundary of the Caribbean, and it extends all the way over to Haiti. And it caused that earthquake in 2010 in Haiti. Yeah, there's a strike slip fault that is on the northern boundary of the Caribbean plate, and the Caribbean plate is moving to the east. Yeah, that's correct. That's a well-known strike slip fault. And the mechanisms tell you about that. Well, we can look at the Earth's interior as well, looking at seismic waves. And here's a beautiful diagram showing many, many rays that traverse the mantle in red, and the core in orange, and the inner core in white, and show up on these wiggle traces that are on the right-hand side. Some are in green if they're a P wave. Double P is a sort of red color, and so on. So seismologists record many, many earthquakes. And by looking at lots of them, we're able to see the structure of the interior of the Earth. For one thing, because the outer core is a liquid and no S waves will travel through a liquid, obviously. So that was one of the first discoveries, was that there was a P wave traveling through the orange region, but there was no S wave traveling through the orange region. The standard model of the Earth is called at the bottom, Preliminary Reference Earth Model, and that is the layering of the Earth. It appears in the book and Carey as well, and generally is characterized by increasing P and S wave velocities down to 2,900 kilometers. And when we hit the Earth's core, and both the S wave goes to zero and the P wave decreases because it's a liquid. And so this reference model took many, many decades to create. It wasn't finalized until about Jeffries and Bullen finalized the model pretty much in the mid-1950s, and then it underwent further refinement finally in 1991 with the standard model. I'm just going to end today's lecture with an example of looking at the structure of the subducting plate at the Tonga Trench. In the blue is the Pacific Ocean, and in orange and yellow and green are the Tonga Ridge and the back arc, the Lau Basin in the back. And we're going to look at the ocean, the Pacific Plate, as it subducts beneath the Tonga Islands. So if you have seismic stations in Tonga and Fiji, that would be the green, and you're trying to image this red mass, you can look at the seismic waves coming from Australia in blue, and they will get a delay time at certain green stations, as you can see. Now, if we have an earthquake coming from South America, now here's a South American earthquake coming from the other direction, and it will have a different pattern of delay. So now we have the blue and the black, and the only way you can get the blue and the black is if you have the anomaly, the delay time, the delay occurring at a certain depth and in a certain geometry. So the relative delay time example shows you that using seismic energy coming from different directions is very informative. And there we have it. This is an image of the subducting plate in blue, positive, cold oceanic plate being pushed down into the mantle, derived from seismic tomography, the delay times that I just explained, and you get the low velocities at the spreading center where magma is coming up to the surface, at high velocities in blue where the subducting plate is going into the mantle. So we can actually prove the geometry predicted by plate tectonics if we have enough seismic data. So thank you for your attention. We've talked today about many topics, and we're ending with the theme of the subduction of oceanic plates at the Tonga-Fiji region, which has been one of the primary study areas in earth science.